In this short video, we're going to look at intermolecular forces and how those intermolecular forces have an effect on the melting point or boiling point of various compounds. Our first question asks, what kinds of intermolecular forces are present in each substance? Here we're looking at whether these molecules are polar and will have dipole-dipole or hydrogen bonding, whether these molecules are nonpolar and will do van der Waals interactions, or whether these compounds are ionic and are held together via ionic bonds. Our first compound is nitrogen trichloride, which we're told has a trigonal pyramidal shape. This tells you that the molecule is going to be polar because it's asymmetrical. Specifically, nitrogen is more electronegative than the chlorines and will be pulling electrons up, creating a slight negative charge at the top of the molecule. The same phenomenon occurs with ammonia, which also has that trigonal pyramidal shape, and the electronegative nitrogen at the top creates a partial negative charge at the top of that molecule. SiH4 is tetrahedral, which is symmetrical, telling us that despite any polarity, and it's small, but despite any polarity in those bonds, there is no overall molecular polarity, and therefore the molecule exhibits van der Waals interactions and not dipole-dipole bonding. This same phenomenon is true with CCl4, carbon tetrachloride. Each of those bonds is quite polar, but because the molecule overall is symmetrical and therefore nonpolar, the molecule exhibits van der Waals interactions. If we keep going, we look at ozone. Ozone is comprised of 3 separate oxygen atoms. None of those atoms are pulling more strongly or more weakly on electrons, and therefore the molecule exhibits no overall polarity, and ozones will interact via van der Waals interactions. HBr is a really good example of a polar molecule. Bromine, while slightly more electronegative than hydrogen, is not electronegative enough to qualify for hydrogen bonding. So even though we have a hydrogen in this molecule, it's going to exhibit a dipole, but not hydrogen bonding. And HBRs will interact via dipole-dipole interactions. Methanol is a great example of a hydrogen bond. An oxygen bonded to a hydrogen will interact with other methanols via hydrogen bonding and create relatively strong interactions between those methanols. Our last molecule here is molecular iodine, I2. I2 is a nonpolar molecule. Those iodines are pulling equally on their electrons, not creating a pole, a dipole, positive or negative side to that iodine, and therefore iodines will be held together via van der Waals interactions. Our next question says, one of these two substances is a liquid at room temperature. The other one is a gas. Which one is a liquid and why? If we look at the parts that are different on these molecules, methanol, as we talked about before, does hydrogen bonding. That hydrogen is bonded to a highly electronegative oxygen. CH3SH is going to be polar, but that SH bond is not polar enough to generate the uniquely strong hydrogen bonds, and therefore will interact with other molecules, other CH3SHs, via simply dipole-dipole interactions. That is a weaker interaction than a hydrogen bond, telling us that CH3SH is going to be a gas at room temperature, whereas methanol will be a liquid at room temperature. A very similar question. A flask contains a mixture of NH3 and CH4. It's cooled. At minus 33.3 Celsius, a liquid begins to form in the flask. What is that liquid? In effect, this question is asking us which one of these compounds has the higher boiling point, because at the higher temperature, it begins to condense into a liquid. Now, we can look at the kind of bonding that these two molecules do. NH3, as we've talked about earlier, is polar and will do some hydrogen bonding. CH4 is symmetrical and will do van der Waals interactions. Van der Waals interactions are significantly weaker than hydrogen bonding, telling us that CH4 will stay a gas at much, much lower temperatures, telling us that at minus 33.3 Celsius, there must be the ammonia that is condensing into a liquid. The last problem in this problem set asks us to list these substances in order of increasing boiling point. What we're looking to do here is to find the substance that has the weakest intermolecular forces, and that will be the lowest boiling point, and then rank them in progressively increasing orders of intermolecular forces, which is again a good proxy for boiling points. Looking at this list, neon atoms will interact with each other via weak van der Waals interactions. That's going to be our lowest intermolecular force. Our next lowest will be SO2, going to interact via some dipole-dipole interactions, but that's going to be weaker than the hydrogen bonding that exists between NH3 and H2Os. Here we can look at the electronegativity difference and see that the difference between nitrogen and hydrogen is less than that between oxygen and hydrogen, telling us that the hydrogen bonds in water are significantly stronger. Lastly, we have NAF, a metal and a nonmetal forming an ionic bond that will have far and away the greatest intermolecular forces and far and away the strongest boiling point. Here again is a good review of intermolecular forces and their effects on boiling points. Thanks for watching.